So today we will be solving the popular LRU cache problem from LeetCode, but we will be doing this in Golang, but we will not be using your traditional approach. We will be using multi-threading, which is the power of Golang, which is what Golang is known for, right? Go routines. So we will be implementing an LRU cache, which is thread safe as well. So come, let's see how to do that. So we go to LeetCode first, we just copy the entire structure of the problem, just paste it in our application in our VS Code, and then it's throwing an error because we have to define a package main. All right, so let's just get rid of this. All right, so how does an LRU cache work? LRU cache is basically a cache which evicts items on the basis of how recently they have been used. So all the most recently used items will be at the front of the cache, and all the least recently used items would be at the back of the cache. And when I say front and back, is basically internally the cache would be using a linked list. So all the items at the front of the linked list will be most recently used, and all the items on the back would be least recently used. So that is how the cache would decide which items to evict. So the eviction will always happen from the back at the end of the linked list. So that's the basic concept. So let's see how to how to implement it in code. So our LRU cache struct will have three things. First would be a mapper. So why do we need a mapper? So the linked list will be storing the actual elements of the cache, but the mapper would map the key to a particular element in the linked list, because linked list uses pointers. So the key in the map would keep a track of the node in the linked list, just to make our lives easier. So that when we want to remove something or delete something, we do not have to traverse the entire linked list. We just keep a pointer to the node and we just remove that node directly. So that's how we are going to do that. So let's see. Key to data mapper, let's call it that. It would be a map of int is the key, and it would be linking to a list element. So in Golang, lists container / list is the implementation of linked list, and each linked list contains an element. The element is basically the node. Linked list node is called element. Okay, and it would be a pointer. We are using pointers just to save unnecessary copy operations. Pointers will pass by reference, and it will save on a lot of performance when it comes to copying and exchanging variables. Okay, key to data mapper. And then the second thing we need is the linked list itself. So let's call it list, which would be let's call it L, or let's call it list. Fine. It would be a pointer to a list, and this list is the actual linked list. So this list is comprised of elements connected by pointers, right? And then we have a capacity, which is basically how many elements you can store in the cache at one point of time, which would again be an integer. Now, moving on. So the constructor should give us a pointer to an object of LRU cache. So Golang doesn't have objects or classes like technically, but here we can use, let's just call it struct. So it will give you a pointer to a struct of LRU cache. So let's return and, which will basically return the address of an LRU cache. That's how you return a pointer. Now we need to initialize the items, the fields. So to initialize a map in Golang, we use the make keyword, which basically allocates memory for this data structure. Similarly for list, we will use the inbuilt list new method, and then for capacity we just use it from the constructor input. So now we have an LRU cache. Now, oh, one more thing. Since this is going to be multi-threaded, we need to ensure that it is thread safe. So we need one more thing here, which is a mutex. So if you guys don't know what mutexes are basically to create locks on resources. So there can be different types of mutexes. We have read mutex, write mutex, read write mutex. So let's see. Let's call it mu, and it should be, oh, not multipart, it should be mu, and it should be sync package mutex. It should be a read write mutex, to be honest. Okay. Yeah. Now we need to create the get function. So when we are trying to get something from the cache, let's say we try to get an element which was on the at the end of the linked list. And using the key, we can easily get the node which is at the end of the linked list. But once you get that node, it becomes the most recently used. So you need to move it to the front of the linked list. So that would be the entire concept of how we are maintaining this LRU property of this cache. So let's see. So the first step would be to check if the key exists in the mapper. If the key doesn't exist, that means this node does not exist in the linked list. So we will do that first. And one more thing, the data that we are storing in these nodes, in these list element containers, it would be a pair of key and value. And why we are using pair, we'll come to this later. But we need to create another struct called pair. This is not C++, so we have to do pretty much everything on our own, which is fun for me actually. Pair struct. And now what we do is we create a key which is an int, and then value which is again an int. Let's call it val, right? Okay. Now what do we have to do? Yeah, so we need to check if the key exists in the mapper. So how do we do that? We do that by checking if element. Okay, so this is the syntax for maps, how we check items in the map. Before checking, so since multiple threads can access this, so we need to use a mutex first before we are trying to read a memory resource. So let's do that first. We will first get a lock, read locker, and then once we get a lock on this resource, we just do mu now. We need to check this dot key dot mapper, the key, we pass in the key here, and then if it is okay, if everything is okay, this element exists, this key exists in the mapper, then we just return the value stored in that node or in that element. If not, we just return -1 as per the implementation of lead code. So now we have found the element or the node in the linked list which is mapped to this particular key. So all we need to do now is to extract the value stored in this element and then return the value. Now, and how do we do that? Extract the value stored in the node slash element. So how do we do that? We do that by, okay, one more thing. We need to first move this element to the front of the linked list because this has become most recently used now. So before we extract the value, let's just do move this element to front of the linked list since it has become most recently used. So how do we do that? We just do this by this dot list move to front. We have a function which takes an element. We just pass in the element. Now this element has been transferred to the front of the linked list, so it is most recently used now. Now we need to extract the value, and how do we do that? We do that by return element.value. We need to typecast it because we are storing a pair. This is basically called typecasting in Golang. So the value can be anything. If I remove this pair, if I hover over this, you can see the value can be anything, but we don't need any. Any is basically not useful for us. We need to typecast this any to the kind of data structure that we have actually stored in the node. The linked list node can store anything because it has generics. It has a support for generics. But here we are particularly storing the pair struct in every node. So we need to typecast this any value to pair. How do we typecast? We typecast it by dot, and then in the brackets we just write the type of the thing that we are looking for, and then the pair has a value, and this is what we return, right? So our work is done. Our get logic is completed. Now comes the more difficult part. How to do the put. So for put, before we do the put function, let's understand. So we need to check first if the key that we are trying to put in the LRU cache, it exists in the mapper or not. If it exists in the mapper, well and good. Just update the value for that key and then move that node to the front of the linked list. As simple as that. But if the key does not exist, we will basically create a new node, put in the value in the node, put in the pair value in the node, and then put this node at the front of the linked list. And then we reduce the capacity because we just filled up a space in the cache. So that's what we are going to do. So the first step is check if this key exists in the mapper. So we again do the same logic. Element, okay, this dot key to mapper key, and if it is okay, then it's fine. Else, if key does not exist, if this key does not exist in the mapper. Now, since let's take the first example, the key exists in the map. So what we need to do is we need to take the element, update its current value, and then move it to the front. So update the current stored value in the node slash element. How do we do that? We do that by element.value dot pair. We need to dereference the pair, store the value as value. So why did we dereference it? Because we are trying to change the data itself. We're not trying to change the reference, the data that is stored in this pair struct. That's what we're trying to change. So we dereferenced it. If we do not dereference it, it will throw an error because now it's no longer referring to the value itself, it's referring to the memory. So we will dereference it. So once you have updated the value stored in the node, now we need to push this node to the front of the linked list. So move this node to front of linked list. How do we do that? Again, we do this by list dot move to front, and just that's it. Your work is done. See how easy Golang makes LRU implementation. Like if I was doing this in C++, I would have had a very tough time. I mean, the syntax, it just makes me go crazy, but this is so beautiful. Okay, now if the key does not exist, so what we need to do is we need to first create the node and then put it in the linked list. So how do we create a node? Let's call it new element and this dot list dot push front. So we are pushing to the front of the linked list because this will be the most recently used. And what are we pushing inside? We are pushing a pair. And what does the pair have? The pair has a key and the pair has a value. Okay, so now we've got the new element. Now this new element will be added to the mapper with this particular key, because we also need to keep a track of which element exists, right? We also need to keep a track of the key to the node mapping. Now we need to update the mapper, this dot key to data mapper, and then we have a key, and this would become new element. So our mapper has been updated as well. Now we need to reduce the capacity because we've just filled up one slot in the cache. So now we reduce the capacity, this dot capacity negative. Now we also need to check one edge condition. If the capacity becomes 0, in that case we need to have the LRU eviction policy taking place. So we need to make a check if this dot capacity becomes negative, like it has become less than 0, sorry. Then what do? We will do, firstly we will take the last element from the linked list and we will delete it from the linked list as well as the mapper. So how do? We check the last element first. How do we do that? This dot list dot back. the back function will return the last element of the linked list. Now we have the element. Now what we do is we remove this element from the mapper first. Let me write this. Get the last element from the linked list. Remove from mapper. So we have a delete keyword to delete the keys in the map. So we just put in the map here, and then now we need to give the element that we need to, not the element, the key that we need to delete. So how do we get the key? So remember, we are storing a pair in the node or the element. So the pair has both the key and the value. So how do we get this? We get this from the last element dot value dot pair dot key. So this will basically give us the key that we need to delete from the mapper. The mapper is gone. And now we need to delete from the linked list as well. So this back function did not delete it. It just gave us the last element. So we need to update our linked list as well. Remove from linked list, this dot list dot remove. There's a remove function and it takes an element. So we just pass in the last element. Now your list has also updated. So your capacity is again back to 0. Right. Okay, we missed one thing. So I told you that this is going to be a multi-threaded application. So we forgot to use mutex. So before we do anything, any put operation, we need to write a mutex. This dot mutex dot lock, we need to achieve a lock, and then we use a defer keyword. This dot mu dot unlock. So this will make our application thread safe. Now, why am I using the defer keyword? The defer keyword basically is a special keyword in Golang, which basically executes at the end of the function. So once your function body has completed, then the defer keyword will be executed. So you don't have to manually remember that you have to release the lock as well. So this keyword helps us with memory management in Golang. With lock management. You don't have to manually remember to get a lock and then release the lock, so that deadlocks don't happen. So this defer keyword is like an excellent feature for Golang, I would say. So this is a good implementation for thread safe Golang code. If you have any doubts, you can reach out to me. I am a Golang enthusiast. I just love this language, and I'm learning myself as well. But I would love to help you out. If you guys have any issues, any understanding issues, any problems with the code, just come reach out to me, and I'll love to help you out. Right? Okay, that's it. Bye. Take care.